Okay, gas laws. So a couple more example problems here. And again, let's try to keep track of how we are approaching figuring out the appropriate equation to use or the right gas law to use. So in this question, we've got a sample of nitrogen gas. It's at 18 degrees Celsius, 760 millimeters of mercury pressure, and the volume of the gas is 3.92 milliliters. We want to know what is the volume at 0 degrees Celsius and 1 atmosphere of pressure. So, like I said before here, there's two circumstances here. So we want to think about what variables are changing, which ones aren't changing. So let's just make two columns here. What's changing, what is not changing. Right? And volume right off the bat is what we're asked to solve for. So we're given a volume, we're solving for a second one. So reasonable to say that volume, if it's not changing, we have to figure that out. All right, so volume is going to change here. The temperature was 18 degrees Celsius. It went to 0, so temperature is changing here as well. What's not changing? Well, it's the same sample of gas, so N's not changing. R never is changing. And if we look a little closer at the pressure here, 760 millimeters of mercury, we said, is 1 atmosphere of pressure. That's actually the relationship between those two. So pressure is not actually changing here. So pressure did not change either. Now, when we get to the end of the problem, I'll go through and show that if you didn't realize pressure wasn't changing, you should still get the same answer for the problem because you want to keep track of your units and eventually those pressures will cancel out. But in this case, V and T are changing, so what we want to do is take our ideal gas law and we want to rearrange it so that V and T are on one side and the non-changing variables are on the other side. So the simplest way to do this would be divide both sides by T, bring T over here on the left with V, and then divide both sides by P. So that would give me V over T is equal to NR over P. Right? And since we said NR and P are all the same here, that would mean V over T is equal to a constant. Right? And that would mean V1 over T1 is equal to the same constant as V2 over T2, and that is my equation. V1 over T1 is equal to V2 over T2. Now, again, I'm solving for volume, so V2 is what I want. I could multiply both sides by T2 and end up with V2 is equal to V1 times T2 over T1, and that would get me to solve for V2. Okay, so again, that's an equation you could memorize, but that doesn't do you a lot of good. You'd still have to figure out that it's the appropriate equation for this problem, and you're going to have to do that about the same way as we're kind of working our way to the equation here. So no real benefit to trying to memorize all the problems. You still have to work your way through and figure out how to apply them. Now, volume is perfectly fine here because it's in milliliters. So when I solve for V2 here, I can plug in 3.92 milliliters. That unit's not going to cancel out, so it's going to stay the same. That means my answer will be in milliliters, but I was just asked for volume. Temperature, though, remember, it's got to be Kelvin. So even though we have T2 on top, T1 on the bottom, we don't get the same relationship with Celsius. So even though it would look like the Celsius would cancel out here and just leave us with milliliters, it will not give us the same answer. These have to be Kelvin temperatures. So T2 0 degrees Celsius would be 273 Kelvin. Again, we're just adding 273 to the Celsius temperature. And then 18 plus 273, I'm going to do that on my calculator just to be safe, would be 291 Kelvin for T1. Right? And now they do cancel out there, and this will give us that second volume in milliliters. So 3.92 times 273 divided by 291. And the second volume here would be 3.68 milliliters. Right? Now notice the relationship here between volume and temperature is a little different than it was between volume and pressure. Because it was P times V, here it's V divided by T. So volume and temperature are directly related in terms of gases. So in this case, from T1 to T2, the temperature went down, and that caused the volume to also go down. So direct relationship between V and T. Now, this problem though, suppose we thought P was changing. If we thought P was changing, so if we have our changing variables as V, T, and P, and our non-changing as just R and N, right? We'd again start with PV equals nRT. We'd rearrange, but we want V, P, and T on one side. So P and V are already there. We'd divide through by T. We'd get PV over T. That would equal NR, which is our constant. So that would equal P2 V2 over T2, right? And one's on the left. So that equation is called the combined gas law. It's really combining the relationship between pressure and volume and the relationship between volume and temperature, right? Or the relationship between pressure and temperature is in there as well. But if we solve that one, again for V2, and multiply both sides by T2, would give us P1, V1, T2, and then divide both sides by P2, we have P2 on the bottom with T1 is equal to V2. Now, you go to plug in these pressures that were given in the problem, right, and the units aren't the same. So you should recognize, well, I'm going to have to change my pressure to millimeters of mercury or my millimeters of mercury to atmospheres to make sure that the units match up. And then those two would be the same on the top and the bottom. That would just cancel out. If you cancel out those pressures, you end up with exactly the same equation we got when we included pressure in the not changing variables. So again, if you're evaluating the problem, you should arrive at the right equation. And if you do miss something that happens to not have changed, it'll cancel out. So this is a pretty good method for going about solving problems here. All right, let's see if we can fit this next one in and not have the video get too long. We want to calculate the number of molecules in a deep breath of air given a volume, 2.25 liters, temperature, and a pressure. So there's V, T, and P, and that means the only thing missing from the ideal gas law is N. So if PV equals nRT, that means N is equal to PV over RT. And if I plug in there with the right sets of units, I can calculate moles, right? And we should remember how to convert from moles to molecules in this sample. So again, I'll start with R, 0.0821 liter atmospheres per Kelvin mole. And that just gives me a nice reminder of the fact that I'm going to need those appropriate units. So if I add 273 to 37, this is 310 Kelvin. Now, we should have a decimal there because it is significant through the ones place, 310 Kelvin. So normal body temperature is 310 Kelvin. The pressure is in millimeters of mercury. We want that to be atmospheres. So let's convert that. 1 atmosphere is 760 millimeters of mercury. So 735 divided by 760. That is 0.9671 atmospheres. And I'm keeping just an extra figure there just to make sure I don't round too much, right? We're really going to end up at 3 here. This is 3 once we convert it to Kelvin, and these are 3 as well. The volume is just fine in liters, 2.25 liters. Now, like we saw before, the units are a little more complicated, but they'll end up just as moles. So, multiply all this out. And that comes out to 0.085. Now, I did round what I wrote down there. I'm actually going to use my calculator here and use the exact number. So we're not rounding it a lot to change it to 55 because it's 497. But again, we don't want to round it all if we don't have to, but you may want to minimize writing everything down every time. So that might be a useful approximation to make, particularly if you keep the regular number in your calculator. If this is how many moles of gas there are, we can use Avogadro's number, or the Avogadro constant, to figure out how many molecules there are, because we know there are 6.022 times 10 to the 23rd molecules in 1 mole. And we don't even have to know what is making up the gas to know that comparison, right? So air is a mixture of primarily nitrogen and oxygen, but probably some CO2, maybe a couple other things in there. But the relationship between moles and molecules doesn't matter what we're talking about. So multiply that previous answer by 6.022 times 10 to the 23rd power. And we get how many molecules are in this deep breath. So now we want 3 sig figs. So 5.15 times 10 to the 22nd power molecules in the breath. So again, we've got 3 variables from the ideal gas law. We just plug into the ideal gas law and make sure that we work all the units out. And we did need that one extra step to get to our final answer, which won't be uncommon when we're doing a kind of a standard ideal gas law problem. Okay, we'll stop the video there. We'll come back. We'll look at a few more issues in gas laws.